In the previous lesson, we learned the definition of matter. In science, matter is anything that has mass and volume. But we left it to be defined exactly what we mean when we say mass and volume. And that's what we're going to do in this lesson. We're going to take a step toward understanding those terms related to matter. We're going to take a step toward understanding the definition of mass. What does it mean when we say that all matter in the universe has been created with the fundamental property characteristic that it has mass? Let's take a look at that term to understand what it means. First off, let's look at the scientific definition of mass. Mass is the amount of matter packed into a substance. Okay, you may realize that there's something a bit circular going on here. We defined matter as anything that has mass and volume, and now we're defining mass as the amount of matter packed into a substance. It's not good to define two terms using each other like that, so we're going to use another word in just a little bit, but for now, think of it as how much stuff is packed into something. The more stuff packed in, the more mass something has. Now, matter is typically measured using one of three common units in science. They are the gram, the milligram, or the kilogram. A gram is a fairly regular measure of mass. A standard size paperclip is about 1 gram. When you look at the nutrition facts for the foods that you eat, you'll see that sugars are measured in grams because usually there's a great deal of sugar added to foods to make it sweet. 1 packet of sugar weighs very roughly 1 gram, to give you an idea of how much mass that is. On the other hand, if you look at those same nutrition facts, you'll see that sodium, or salt, is usually measured in milligrams, because you need a lot less salt in your diet, and you can handle a lot less than you can handle sugar. A milligram is 1/1000th of a gram. So I want you to think of the mass of that sugar packet as 1 gram. 1 milligram of sodium would have a mass that's 1/1000th the size of a sugar packet. It's a very tiny measure used to measure very tiny amounts of a substance. And then there's also the kilogram, which is used to measure large objects or larger substances. Kilograms may be a common scientific measure for human weights, for example, or for cars. Or you can even express the mass of much, much larger objects like the entire Earth as a large number of kilograms. Now, of these three units, the most commonly used and therefore the scientific standard unit of mass is the kilogram. Most often in science, you'll see masses expressed as kilograms. It's the standard unit. Now let's go back to the definition of mass, the amount of matter packed into something. I want you to think of 3 different objects and how much matter might be packed into them. First off, let's look at weights that you might lift. Different size lifting weights have different amounts of matter packed inside, such that lighter weights have less matter packed into them, so they resist your motion less, and larger weights have more matter packed inside, so they resist motion more and make your muscles work harder. Now I want you to compare the masses, the amount of matter packed into these lifting weights, compared to the amount of matter packed into an entire car. If you've ever had to push a car because it died, it's not a very pleasant experience. They are very difficult to move. They have a lot of mass, especially in the engine where there's just a whole lot of heavier metals that have a lot of stuff packed into them. Now, as we're comparing objects, you'll notice a trend. The amount of matter packed into smaller objects tends to be less than the amount of matter packed into larger objects. And now I want you to consider an even larger object. How about the entire moon? The moon has a lot of matter packed into it because it is such an immensely large object. So here we see a pattern that if you didn't think about it, you might think that this applies in all cases. We see that the bigger an object is, the more mass it's likely to have. But that's not always the case. What if we consider 2 objects that are exactly the same size? like this lump of coal and this piece of lead ore. Which is going to be more massive, the coal or the lead? If you had one in each hand, you would realize that coal really doesn't have a lot of mass to it. It's pretty light and easy to lift. It doesn't resist you moving it all that much. Whereas lead is very dense and heavy, and it does resist moving it. It really makes your muscles work hard. So how can two objects of the same size have different amounts of mass? How can one have more matter packed into it than the other? Well, to understand that, we have to actually look at the smallest pieces of matter, that is, the atoms that make up a substance. Now, I want you to take a look at this statement about mass, because this looks a lot like the previous definition, except I changed one part. I added a word. Mass can be thought of as the amount of atoms packed into a substance. Now we're getting a little bit clearer than just saying it's the amount of matter or the amount of stuff packed into a substance. It has to do with atoms, which are the smallest fundamental unit of matter. If we could magnify matter so we could see its smallest pieces, those smallest fundamental basic pieces that make up that type of matter are atoms. Now let's take a look at what that means for real substances. Here's a chunk of gold. And if we were to magnify a chunk of gold so we could see its atoms, it might look something like this. Notice that gold has large atoms and they are extremely closely packed together, which means that gold is probably going to have a lot of mass. Even a small piece of gold, because the atoms are so packed tightly in, will have a lot of stuff inside it. It will have a lot of mass. Now here's something kind of interesting. We have this listing of all of the known elements in the universe. We call that the periodic table of elements. As you go farther down and across on the periodic table, the atoms that are located farther down and across are actually bigger than atoms that are near the top and on the left. If we look at where gold is on the periodic table, we realize that it's near the bottom, so it has some pretty hefty atoms. The size of the atoms matter, and the closeness that the atoms are able to pack together matters for how massive an object is going to be. So gold, even if you have a small piece, is able to have a huge amount of matter packed into it that makes it very massive. So what about those two substances we were looking at before, our chunk of coal and our chunk of lead ore? Well, let's take a look at the atoms in those. Here's our coal, and coal is made up mostly of carbon atoms, and those carbon atoms arrange themselves so they're fairly spread apart, and carbon atoms are very small. They're located near the top of the periodic table. Even if you did have a lot of atoms, those atoms are so small and spread out that really coal is a very light substance overall. And then there's lead, which has smaller atoms than gold, but those smaller atoms are able to pack in closely enough together that even a small piece of lead is probably going to have a pretty big mass. Not as massive as gold would be, because gold's atoms are bigger and more tightly packed, but lead's atoms aren't pipsqueaks either. Now, one more question. Is it safe to say that lead is more massive than coal? Not at all. You could have a tiny, tiny, tiny nugget of lead and a huge room-sized vein of coal, and because the coal is larger, it's going to have more stuff packed into it than the lead, even though the lead has bigger atoms. Just because a substance has closer packed atoms doesn't necessarily make it more massive than another substance with more spread out atoms. What if you just have a huge sample of that other substance? So that's the definition of mass. Mass is how much matter is packed into a substance based on the way the atoms are packed together. Remember, mass depends on a few things. It depends how big the object is, it depends on how big the atoms of the object are, and it depends on how closely those atoms are packed together inside the object.